Welcome back. Now we go for the next uh, scenario, so to speak. We're going to talk about the hyperplane-based classifiers. Actually, this is the foundation for the support vector machines. Now we indeed start with the support vector machines. Okay, we're going to look for the best as possible hyperplane in this formulation, which is the one that divides at the middle, at the center, two sets, one with the positives and another with the negative elements. We're going to start like this. Consider this space in which we've got the green elements representing the positive examples, and the red elements as the negative elements in my space. I'm working in R2, so my space is a typical bidimensional space. I could say this is, as before, like temperature, and this is like pressure, or maybe a different variable. Okay. At this point, I have like one first consideration. I need to state that I've got two support hyperplanes. This is the support hyperplane defining the positive class, and the support hyperplane defining the negative class. What do they mean? They mean that after this hyperplane, I only have positive elements, and after this, I only have negative elements. Of course, if my space is not enough, I should come up with some kernel transformation. And I hope to find my best as possible hyperplane at this point. Why it is important to find this hyperplane? Guys, if you don't remember, go back to the generalization bound and to the large margin bound. The large margin bound is the one defining that the scattering coefficient for the support vector machine will be the smallest open ball, the radius of the smallest open ball enclosing all data points, to the square divided by rho, which is the margin, this margin over here, to the square, times log of n to the square. So the greater this margin is, the better is going to be for my scattering coefficient, because it's going to be smaller. And of course, that impacts the uniform convergence and makes my algorithm, my classification algorithm, it just provides like greater learning bounds, or tighter if you prefer learning bounds, or if you prefer stronger learning bounds. They can be used as synonyms over here, okay? There is like a trick over here to consider. This point from the positive class, which is the closest to the hyperplane, should be classified as positive 1. Those points which are the closest to the hyperplane from the negative side should be classified as -1. Those points which are far from the hyperplane would have on this side a negative sign, on this side a positive sign, but with a greater magnitude. This means if this one is +1, this could be like +2. If this is like -1, this should be like -2 or -3 or -4, but a number whose absolute value is greater. Absolute value, okay? I'm just going to start here. Consider I have two position vectors. A first position vector defining this positive point on which my support hyperplane for the positive class lies on. Okay? And here I have a negative position vector on which my hyperplane defining my support hyperplane defining the closest negative elements R lies on. Okay. On top of that, how could I come up with the solution of the margin I have for this problem? What is the best margin if my sample is exactly this sample? This hyperplane could be cutting like here. No, it could be cutting like here. No, this hyperplane should be at the center, at the middle. Why? Because it will provide the greatest as possible margin from the hyperplane to the positive element and from the hyperplane to the negative element. Okay? So what I do now is exactly algebraically, how can I solve this and find this margin over here? It's not difficult. I just have to remember projections. If you guys remember projections, it's going to be so way easy. For instance, if I take this positive position vector minus the negative position vector, I will have this red vector. Positive position vector minus negative position vector will be this red vector. Okay? This red vector has some, let's say, some angle that's not actually orthogonal to those support vectors. It's got like some different angle. Because it's got some different angle, this distance will be greater than the distance from this point over here to this point over there, touching on the second support hyperplane. So what I'm going to do now is project this red vector onto this V unitary vector. This is basically a unitary vector. How can I perform that projection? Algebraically, we typically write like this: the projection of the subtraction of my positive position vector minus the negative position vector. In terms of V, I will project it on V, okay? The projection is just the inner product or the dot product. So I compute the dot product of my x plus minus x minus with V. And I will proceed with this projection, okay? This V is a unitary vector that I simply don't know. But what's interesting? It's interesting that I can define it. I can just define that. I can call V as W divided by the norm of W. This means that my vector W now will be a vector whose length can be greater than 1 or smaller than 1. So it's not unitary. It's not unitary. So when I divide it by its length, it's going to be a unitary vector. So V, which is a unitary vector, is W divided by the norm of W. And I just proceeded with this substitution over here, okay? Just that substitution only. Now I can distribute this formulation. I can just do something like this. As this is a linear transformation in my dot product, I can just define the inner product of my positive position vector by this unitary vector, like this. This minus sign appears here, the negative position vector, inner product or dot product with my unitary vector, like this. How can I solve this? This is not difficult to solve. You know why? I gave you guys a very nice concept before, but it was not formalized yet. I just told you guys, okay, the closest positive point should be classified as positive 1, and the closest negative point should be classified as minus 1. How can I do that? I can do that by defining some constraint for our problem. This is a constraint. Let's see what happens with this constraint over here. Let's suppose, I could open VIM like this, just to show you. What I want to do is exactly this. When you guys provide some vector that I just don't know, I want to compute its inner product, dot product, with my vector w plus some b, as I showed you guys before. You guys remember that this w was c plus in the other example and c minus in the other example in the previous video, of course. In this case, I will have just a single vector called w representing both. Just easier, of course. So if I compute the inner product of this vector by some element, any kind of element in my sample, let's say this is the closest positive point, okay? Plus some b, my result should be positive 1. If I compute the same, but for the closest negative element, my result should be what? Negative 1. You know what's interesting over here? I can rewrite that. I can just write it in a different way. Here, of course, my class, the class I expect is the positive class. And here, the class I expect is exactly the negative class. So I can take both over here, like this, and perform some quite nice product. I can just multiply here for the positive element. All this term by the positive element, and plus 1 times the positive element. And on this side, I can do the same for the negative label times this, and here the same times the negative label. Of course, this will have quite a simple result. On the right side, if I have something plus 1 times plus 1, it will be 1. Negative 1 times negative 1 will be positive 1. And I can generalize this quite simple formulation. Generalizing, I can say you something. I can tell you that it doesn't matter the class I have, it will be a class for any instance yi times the inner product of w by xy plus b will be equals to 1, like this. And you know what's interesting, and quite interesting, is this. I can take advantage of this to solve this problem here. How? Not too difficult. Let's go to the next slide. What I'm going to do is exactly this. If this is my result, what happens when I'm solving it for the positive element? And what happens when I'm solving it for the negative element? Remember that over here on top of this, I'm solving the dot product of a positive element by w and the dot product of a negative element by w. Those two scenarios can be generalized as the dot products divided by this norm. The dot products divided by this norm. The norm can be outside the dot product, dividing the dot products. Okay, this and this. What is the result, obviously, of x plus w? If this is x plus, take a look. If this is x plus w plus b, this result will, of course, be what? Will be the same as w, x plus b equals 1. Because w on this side is positive. So if it's positive, this is going to be the result. Okay? Oops. Okay? And from this, what I can conclude? I can conclude that w dot product with my x plus will be equals to 1 minus b. Take a look over here. X plus w, 1 minus b over here. Okay? 1 minus b. What happens with the second constraint, the second restriction I've got from my problem? If I am computing this w x minus for the negative class, this will be what? Take a look. This will be the same as, of course, I will multiply this side by, yeah, I can just take advantage of this if you guys prefer, or maybe of this, even better. Just look at this, okay? This will be minus 1 minus b. It's not difficult to notice. Minus 1 minus b. And you guys can see here, minus 1 minus b. Okay? I'm going to increase the size. So 1 minus b, coming from the restriction in terms of the positive elements, and minus 1 minus b coming from the negative restriction. 1 minus b, minus 1 minus b. Of course, there is a negative sign here. It is maintained. So I will have what? 1 minus b minus minus 1. This is positive 1. Minus minus b will be positive b. This b and this b will cancel out. And we will have 2. 2 over w. So this is the projection at this point. 2 over w. Here I have that result I showed you guys in the VIM, just using VIM. Again, for the positive case, I'll have this minus 1 on the other side, 1 minus b, okay, minus this b. And for this, it will be minus this guy equals to 1 plus b, because this b is going to the other side. It's not minus on this side because of this. And then it will be positive, of course, if this turns out to be multiplied by minus 1 on this side, and that side will be minus 1 minus b. And this is the result we've got until now. And this is the problem, actually, we have to solve, to optimize, to solve the support vector machine. So the support vector machine looks for the maximization of this projection. By maximizing this projection, we maximize the margin. We increase the distance from the hyperplane to the closest point from the positive, on the positive side, and from the hyperplane to the negative, the closest point on the negative side. Okay? Given this constraint, the constraint, you guys might notice that the constraint now is not just equals to 1 here, but greater than or equals to 1. Why? If you guys remember, I just told you at this point, I didn't show you that this point, this one will be classified, I expect it to be classified as plus 1, those as minus 1. But this one will be minus a greater magnitude. If this is minus 1, this could be like minus 1.5. If this is positive 1, this should be positive 1.5, for example, because they are just far, or at least they've got a greater distance from the hyperplane. So the absolute value, absolute distance of those points will be greater. Okay? So going back, let's see over here. So this is the problem we have to solve. You know what's going to happen in the next videos, next classes, we will solve this optimization problem. It is not an easy problem to solve. It's not. I can tell you, it is not. We're going to see. But anyway, I'm going to show you guys a way of rewriting my problem. Instead of maximizing this problem, which is the same I showed you and we found together after the projection, I can just change it. I can invert. I can use W, the norm of W on top and 2 dividing. So norm of W divided by 2. That's a possible way of rewriting my problem. So if I intended to maximize this, when I do the inversion, when the norm of W comes on top and 2 comes as denominator, I I have to change the nature of my problem. So if my problem was to maximize, when I change that, it will be a minimization problem. Forget this 2, please. Forget it for now. So 1/2 times my norm, forget 2, will be the same, minimizing will be the same as maximizing 2 divided by the norm. Just because I inverted this, it will be the same result. How can I understand that? Just getting back here to R, just imagine I've got like some values over here, like some x varying from, could be like from 1 to 10, in 100 values is okay. This is going to be my norm. When I divide 2 divided by the norm, take a look, I'll have a result like this. If I want to maximize, I want results going closer to a small value, as you might notice over here, okay? Small value. But of course, I cannot go to an infinitesimal value too close to 0 because I have still to satisfy this constraint. If the constraint is not satisfied, I cannot solve my problem. So I have to reduce the norm of W as much as possible while still satisfying this constraint, or these actually, because we've got like one for the positive, one for the negative, actually for every point in my space. When I solve the minimization of the norm divided by 2, I will have the inverse problem. Let's plot it like this, using points in a different color. Take a look. I'll just have a different function, as you guys might notice here. The function goes here, goes like this, okay? So take a look. If here I'm maximizing and I'm reducing the norm, if here I'm minimizing, I am reducing the norm as well. So the problems are equivalent. When I add up this to the square over here, what I do is exactly this. I'm going to power this to the square. When I powered it to the square, let's plot with a green color. Yeah, sorry, the green color. Yeah, like here. This is the function to the square. Okay, what's going to happen? Mathematically, it turns out to be the same. When I reduce over here my norm, it will minimize as well. So mathematically, this will provide the same solution as this without this 2, and the same solution as this maximization. The same solutions. 3 different ways of writing the same problem. The question is why we add up this power to 2, because this will make a lot easier to solve this problem, because it will become a convex surface, and convex surfaces take advantage of a bunch of optimization tools that we can use. That bunch of optimization tools are going to see in the next videos. Okay? That's all for now, guys. Thank you. See you.